Okay, I'm just gonna quickly go over what we've already done leading up to this low division. Some people have trouble with some of the harder factoring problems. Everybody got the easier ones. Okay, so a method that kind of always works, if it's going to work, is to list all possible ways that the factors could be represented. Okay, so what we did was we started out with just multiplying two binomials here, and we got a result here. It just coincidentally turned out to be kind of a difference of two squares. If we factor out 24, we get 4x squared minus 1 here. And then we can factor 4x squared minus 1. We factor 4x squared minus 1. Well, let's pretend we don't know how that factors. And maybe we don't, because maybe we're not thinking in terms of difference of two squares and it doesn't occur to us. So we could write 4x plus 1, x minus 1. And we just start out by inputting 4x here and x here, and then see what numbers fill in here. If we do that and we find that, well, that gives us 4x squared minus 3x minus 1. If we put the minus 1 here and the plus 1 here, we get 4x squared plus 3x minus 1. Doesn't work. We always get an x term, and this doesn't have an x. Then we try the next thing, which would be to put a 2x here and a 2x here. And we put a negative 1 here and 1 here. And of course, that's the same as putting a 1 here and a negative 1 here, because you got 2x sitting there in both terms. So that's the only possibility if this thing is going to factor with integers. Okay, either you got 4x here and x here, or you got 2x here and 2x here. If you got 2x here, 4x and x didn't work, 2x is going to work. You put negative 1 here plus 1 here, you're going to get a negative 2x and a plus 2x. And of course, we already know that when you multiply 2x by 2x, you get 4x squared, negative 1. And 1 gives you 4x squared. So I'll write this as 4x squared plus 0x minus 1, which is 4x squared minus 1. So that now we see that this is 24 times 2x minus 1 times 2x plus 1. Now we did the same thing with this thing. We multiplied this out, we got this. So if you don't factor out the 16, you're kind of stuck with a lot of possibilities. And well, you have 96x with x, 48x with 2x, 24x with 4x, 16x with 6x, 12x with 8x. All that gives you your 96x squared. Then you have to have two numbers here that multiply out to negative 32. So we could start by trying this possibility. Well, you could have plus 32 and minus 1. It's not going to work. Okay. Because you're going to get a negative 96x with 32x. That isn't going to give you 16x. That gives you 64x, negative 64x. And this one, you can see, would give you plus 64x, which would be this. It's not going to be 16x. So we dismiss this. Why do we dismiss it? We dismiss it because any other number, any other way of breaking this down is going to give you an even bigger number over here. And having a bigger number over here along with that 96 isn't going to be very conducive to getting only 16x. Okay. If we have just 2 here, we have 192x. Nothing's going to go here that does anything with that. So we can dismiss this possibility. Okay, well, then we look at possibilities for the second breakdown with 48x and 2x, and we kind of hit the jackpot on that one. Okay, just lucky. But if we use negative 1 and 32, well, no way. 32 times 48x. What in the world is that going to be? Well, that's going to be oh, come on now. Let's 16,390, something like that. Can't think that apart. No, it isn't. It's not a power of 2. So it's 3 times 2 to the 6. Not getting enough sleep, my brain's not working. Okay, so I don't want to think that hard, but there it is. Okay, so anyhow, we dismissed that. Yeah, and we even, but then we look at this one where the 32 goes here and the -1 goes here, and we see we get a negative. Uh-oh. Yeah, we get a negative 48x and 64x gives 16x. Okay. I'll put a check mark there. Not going to write it all out. Now, if we had been smart, we would have factored out the monomial first. 16 times this. This is going to be much easier. There's still a lot of possibilities, but not nearly as many. And the numbers are small too. Okay. Well, that's that. Now, let's do a long division. I'm going to go ahead and do this one for you. Going to divide x minus 1 into this. And well, the divisor has to be something that multiplies this to give you this. So in order to get 96x squared, you better have a 96x on it. Because the only way you're going to get an x squared by multiplying this by this is to have a 96x on it. Well, that's the logic behind it. Now, the way you usually taught to do it, you divide this into this, gives you this. Okay. But then you can also say, well, this times this is better equal this. What do I put here? Multiply by this, it's going to equal this. See it either way, and I don't really have a preference. Okay, now the key here, in the point where everybody tends to make mistakes, including me if I'm not careful, is you got to subtract these. Okay, because you've already got, by having a 96x here, you've already got 96x squared minus 96x. So you take that out of what you have here, meaning you subtract it. And you put a little minus here and a little plus here to remind you of what you're really going to do, because when you see this, you're going to want to subtract 96x from 16x. Okay. And that's not going to work out for you. So you're going to get 0 plus 112x. Well, if you need to get 112x with a constant term here, well, this term had better be plus 112. So we multiply 112 by x, you get 112x minus 112. Okay, well, you've got 112x accounted for here. So that's going to be what you have for x. But that's also going to leave you a bunch of numbers left over, because you only need 32 here. If you multiply 112 by -1, you get negative 112. So we're going to have to subtract negative 112 from the negative 32 that we've got. And that's going to give us 0x plus 80. Now, if I did my arithmetic right, we see that they have a remainder of 80, or 96x plus 112 plus 80 over x minus 1. Well, that's the process. You got your rules. And the process is actually very simple if you remember about your signs. Now let's just make sure this works. Check. check this times this. Use the distributive law. And there we have it. And that's 96x squared minus 96x plus 112x minus 1 plus 80. And that's minus 112, let's see. 96x squared plus 16x minus 32. And it works. Now let me make one other observation related to something that's going to be coming up within the next week or so. If we were to graph this, and graph of 96x plus 112 would have a y-intercept of 112. And a slope of 96. Using my convention, I just indicate slope of 96 for the rectangular box. Okay. So this is graph of 96x plus 112. What's a graph of 80 over x minus 1 look like? It's related to what basic function? So 80 over x minus 1 would be your basic reciprocal function, vertically stretched by a factor of 80. Makes it really tall and skinny. Okay, except the scale of the graph goes all the way up to 112. Okay, and 1 would actually be, well, when you come over to x equals 1, because you're, okay, again, your transformation includes a horizontal shift of plus 1 unit. So your asymptote's going to be out here at x equals 1. Well, where is x equal 1 on this graph? If x equals 1, this is equal to 96 plus 112, right? So that's like 208. So this thing's going to double. So 1's going to have to be out here someplace. Excuse me. And your graph is going to end up something like this. And it's symmetric on the other side. That'll be something like this. When you combine these two graphs, what happens? Well, this one goes to infinity or negative infinity. As you approach the asymptote from the left, it goes to positive infinity here. Okay, this one just keeps climbing at a rate of 96, the slope of 96, and it never goes to infinity unless you go all the way out there toward infinity. So that the infinity, you get here, the negative infinity you get here is going to fairly quickly overwhelm this linear function. So you're going to end up, and you don't have to totally understand this, but you're going to end up with a function that pretty much is going to look like this. And I've got it too close to the asymptote here. But then it's going to just keep going up over here. So it's going to come down kind of infinity, and then it's going to turn around and go back up. You don't have to understand all that. The thing you do want to understand is that you're going to combine like this function and this function to get a graph that does this sort of thing. It has to have an asymptote here because this thing stays finite everywhere in the vicinity of x equals 1. And we're going to be studying functions like that. So you have to become somewhat adept at manipulating expressions like this. Okay, so log division is a good start. Now, another good thing about log division is well, we're going to do another log division. Okay. Why don't we use those? Others. Missed some. It's okay. Okay. Looking, make sure we're done the right thing here, and on the other side here. Okay. Same thing, and we're going to divide this by x minus 1. So go ahead and see if you can do that. Okay, so the log division is fairly straightforward. We're going to get a 48x here because 48x times 2x gives us 96x squared. Then it's going to be minus 48x. And then we have to remember that we subtract this. And this is a 64x minus 32, 2x. But we multiply by 2x to get 64x, well, it's 32. Get 64x minus 32, and that subtracts off. Which will be minus this and plus this. But we really don't have to do that once we get used to the system, because we know if this matches this, then when we subtract this, we're going to get 0. Okay. And then verify, we don't really need to because when we factor this, this is what we discovered. But let's just do 2x minus 1 times 48x plus 32. That equals 2x times 48x plus 32 minus 1 times 48x plus 32, which is going to give us 96x squared. That's 64x minus 48x minus 32, which is 96x squared plus 32x plus 16x minus 32. Okay, well, it's a little bonus here. And we're anticipating what's coming. You got this done, you're good on it. So the more we can get you a little bit ahead on what's coming up in the pre-calculus course, the better. We solve the equation. -6x squared plus 16x minus 32 equals 0. Well, we could plug in to the quadratic formula. But we're going to first divide both sides by 16 because that's going to make the numbers less. And the solutions are going to be the same. If this equals 0, then 1/16 of this equals 0. And 1/16 of this is 9x or 6x squared plus x minus 2. This has the same solutions because, again, if something is equal to 0, 1/16 of that something is equal to 0. Okay, and then we get x equals -1 plus or minus the square root of 1. And minus 4ac is going to be 48 over 2 times 6, which is -1 plus or minus 7 over 12. Now I'm skipping some stuff, the arithmetic, but that's 48. 1 and 48 is 49, the square root of 49 is 7. And that's going to give us what? It's going to give us -1 minus 7 over 12. I'll write it out, -8 over 12, which is -2/3, or 6 over 12 equals 1/2. Okay, so I'm not going to talk any about the details in here because everybody here is just fine with those details, so it's not an issue. Okay, I've gone on with this. An alternative solution we could get this. Now, we would have been better off to divide through by 16, so we only have to factor this. But let's just say we didn't notice that there was a common factor, we got careless, and we got this pass. Well, it doesn't matter. Okay, the only way two quantities multiplied by each other can be zeros if one of them is 0. Then we get x here, x equals 1/2, or x equals I got worried there for a minute. I copied down what I did over there without thinking, because of course we had accident. And if I had any working memory this morning, I'd have known that. Okay, so we have 48x plus 32, and this gives us x equals negative 2/3. And solving these two equations is almost trivial. It's not going to give you any trouble. That's all the same as the quadratic formula gave you. Better solution, here it is, divide both sides by 16. As we did here, you get 6x squared plus x minus 2, which is going to give you well, that'll be 3x and x, and it had better be, you need a plus x here, so you have a plus 1 here and a minus 2 here. It's 2x plus 1. Okay. So this gives you okay, gives you 3x plus 2 equals 0, and 2x minus 1 equals 0. And without writing out the details, the solution set is again negative 2/3, 1/2. Okay. So quadratic formula gives us this. Factoring gives us the same thing. And factoring the way we really should have, dividing out the biggest possible monomial. Leaves us an equation that we can solve also by factoring. I can make kind of a general statement here. You don't need this for the given homework. Okay. Let's look at two x divides this, so 2x minus 1. Need to write the f on of before I write the 9 of 96. I think I know that. To do this. Okay. Factor of 2x minus 1 equals 0 yields a solution of this equation. Since this can be written as 2x minus 1 times something else. Okay. We conclude that x equals 1/2 is a solution. Without finding the other factor. Now, if we do the long division, of course, we get the other factor. But it's kind of worth observing this. So this tells us, for example, we don't have enough time. I'm not going to go into the rest of that. But this leads us to a section that's coming up a little later that we'll probably touch on. I don't consider it to be particularly important in this course because the chances of anybody in this course ever needing to use it in anything but a math course is practically zero. And if somebody would, for example, if you decided to become an engineer, and I can't say that you don't have the ability to do that, can't say that you do, we haven't seen enough, but you certainly have the work habits, okay? If you decided to become an engineer, in some of your later math courses, there's a theorem that's related to what I just did here. If you know this, it's so easy and so obvious that you can learn it in 2 minutes when you need it. Okay. And if you see somebody do it, you just look it up. Rational roots theorem or factor theorem or whatever. And then there's a set of theorems. It's kind of neat. It's really neat stuff. I really like it. But there are other things that people have trouble with that I just don't want to spend much time on. That I don't want to spend much time on. That's you need to focus on other things that are going to be more relevant. And I don't think it's going to cost anybody anything if they don't know these theorems. I didn't know them until I encountered them in an abstract algebra course late in my undergraduate courses. Okay, I didn't need them. And unless you're working a lot with polynomials, you're never going to need them. Okay. So we don't do that. Now, one thing we do want to do today is look at graphs of polynomial functions. Okay. You get polynomial functions by adding power functions. Power functions all have very smooth curves. You know, the squared curve looks like this. The cube curve looks like this. The fourth power curve looks a lot like the square curve, except it's steeper and flatter toward the middle. Okay. The fifth power looks just like the cube curve, except it's steeper on the ends and flatter in the middle. And the higher the power, the flatter they get in the middle and the steeper they get away from the middle. Okay. They're all smooth curves though. They never totally flatten out. They're smooth as everyone. Okay, so what happens when you add these things? And I don't want to demonstrate addition of complicated graphs. They're not that complicated. We looked at a little bit of it, I think, for calculus. Okay, but okay. If you have a polynomial function and it's in factored form, and I'm not going to ask you to do a lot of factoring of polynomials. just a little bit, so you kind of know how it works, because again, it's something that you never can factor a polynomial that occurs in the real world. Okay? And all the tricks for factoring are pretty straightforward to somebody who's going to pursue anything beyond a calculus course, okay? Or is going to use, first year calculus, who's going to use a lot of mathematics in a more theoretical situation, okay? So most of this stuff is useless. However, shapes of the graph might be useless to most people, but it really helps you understand graphs better, and the graphs that you are going to run into in calculus. Okay, I'll give you a little preview of that. And I wouldn't do it if everybody was here today, but it's good for everybody, okay? And, there might be people having other problems that we need to address, but they're not here. So we're able to do a little bit more. Okay. Okay, so if I've got a polynomial, and I know that the thing goes to infinity on this side, and we learned how to do that just by looking at the leading term, the highest power of the polynomial, and asking, is it even or odd? Okay. And does it have a plus or minus sign in front of it? And then we can determine what happens in the long run to the left and in the long run to the right. So if we know that we have 3 zeros and we know that the y-intercept is here and that the graph is up over here, and let's say that we also know that it's up over here. Okay, so long run goes to positive infinity, goes to positive infinity. Then we can sketch a reasonable graph that fits this structure. So it'll probably be something like this. That's probably not a good graph. It probably peaks on the left here. Maybe not. Uh-oh. That didn't work, did it? What's wrong with that? What's wrong with it is it went through the x-axis here. This is not a zero because we know all the zeros, only 3 zeros. Dang. You go through the x-axis, well, you got a 0 there. Okay. So we'll color circle your x around this and an arrow to this point. These are our zeros. We found all our zeros. Okay. So what are we going to do about that? We've already determined it has to go up here and up there. Well, we can fix it in one of 3 ways. The picture's probably going to get a little cluttered up. But we could, for example, come down here. Hit the 0 here. Well, we just fixed it. Maybe. Now, if we look really, really close, if we zoom in on this point here, okay? And we zoom into a little picture, a millimeter on a side, but we blow it up so it looks really big. What's this graph going to look like in that picture? It's going to look like a straight line, because in a small region around this point where it intersects the x-axis, it's practically straight. It doesn't change its slope much at all. Okay. And here, same thing. Okay. So I say it's locally linear. That means you can make it as linear as you want by zooming in far enough. What about this one? What's this look like if you zoom in? Okay, and what basic function is that? Well, don't say it, but you know, it's the squaring function. Okay. It acts like a parabola here, like a shifted and stretched squaring function if you zoom in. So I say the function is locally quadratic here. Okay. If it's locally quadratic here, well, now let's put some numbers in. Let's say this is -3, and this is -1, and this is 4. Okay. Wrote that word fixed really poorly, but it says it's fixed if that's not -1, obviously it's 1. It's fixed if the function p of x for polynomial is some multiple of x plus 3 squared. Because if it's a multiple of x plus 3 squared, that means when x equals close to x equals -3, this thing's going to act quadratic. It's going to act like a parabola. Okay. And then times x minus 1, because when you're close to x equals 1, this just acts like a multiple of the x minus 1 function. And when you're close to x equals 4, this acts like a multiple of the x minus 4 function. Okay. Now, how do you determine A? Well, that's not what I really want to talk about, but I'll just say you determine A because if you know the coordinates at this point, you can plug them in for x. Well, you plug x equals 0 in here, okay? And you're going to get 3 squared, which is 9, times -1, which is going to give you -9, times -4, it's going to give you 36, okay? So you'd have A times 36 equals whatever the thing equals here, and you can solve for A. And you've done that sort of thing. It's really easy once you get used to the idea. And it takes a little getting used to. It's not an obvious idea until it becomes obvious. Okay. So in this case, we say that the 0 at x equals 3 has multiplicity 2. Because it comes from x plus 3 squared, because it's quadratic. Okay. If it's a straight line through these things, then it's multiplicity 1. And if it acts like a cube, if it flattens out, but then goes on up through the axis instead of just coming down and touching it, it's probably a cube. For the sake of this course, it's probably a cube. Okay. Now, it would also be possible that this is a little flatter here and it's really a fourth power of x plus 3. Okay. You don't know if it's a square or a fourth power. You don't know exactly how to draw it. If it's a fourth power, it's going to be a little flatter here. It's going to go up a little higher here. Well, you don't have to know that. Okay. But you can kind of conclude it if you think about it. But what you do know is if it only touches here, it's some even power of x plus 3. Could be any even power. And when you get this graph, just know where the zeros are. Well, it's obviously these zeros are linear, just the first power. So you have one question on the assignment for this course, the support course, that talks about the multiplicity of the zeros and it gives you some polynomial. And there's no video on it. So if you don't get it, okay. But I've just given you enough information that maybe you can get it. Okay, fair enough. And I don't know why I put that up there without a video. It is there and it was too late to change it because some people already started working on it.